Okay, so first up, in one of our contributed talks, we have Roberta Paladini from Caltech IPAC. Thank you.
Okay, so you can click ahead with this one, and then you have to press and hold, and it shows up here.
Okay, thank you. So, hello everybody, and thank you to the SOC for allowing me to present today this talk. So I'm going to talk today about the Roman Galactic Plane Survey, and probably by now everybody knows what the Galactic Plane Survey is. So the 75% of the Roman time would be used by the three core community surveys, but in the first 2 years there will be also a large astrophysical survey that will be executed. This is also a community survey. And it's the survey of the galactic plane. So I was, for full disclosure, I was part of the definition of this of the survey, and the committee was chaired by Bob Benjamin and Rachel Street. And here is the list of all the other members of the committee. So. For anybody who wants to read the full report and all the details, this is online on the NASA website, the Roman NASA website. So I'm going to start immediately saying that this is going to be a great survey producing at least 20 billion sources, although the estimate is very, very uncertain because all our stellar population synthesis models are basically not really exact, especially when we go towards, for example, the bulge, but also in other regions of the galaxy. And so this number actually is, we came up with this number a little bit hand-waving, to be honest. But there will be many, many sources coming out from this program. Now, the survey in a nutshell. So this is a figure from the report that shows the coverage of the survey. So it's, again, the galactic plane, roughly from minus 60 degrees to 80 degrees. The asymmetry is due to the fact that in the first quadrant, we wanted to fully cover the Carina star-forming region. And the survey is basically made up of three components. So the first component that you see here on the left.
Just a second.
Thank you.
Is this the one?
Yes. So maybe you can just use that just to make sure.
This one?
Yes. Okay. Thank you. So the first component is the one on the left. So this is the major component that will be executed with the WFI instrument in 4 filters. Roughly, these are basically the JH and K plus the F184 filter, and it's a coverage of 691 square degrees. Then the second component is a time domain component. These are 7 fields. This is roughly 20 square degrees. And the third component is a spectroscopic component with 15 fields distributed along the galactic plane, trying to sample different extinction and extinction regions and source density regions. Okay, so this talk is about dust, though. So I think it's important to say that when we started looking at the definition of the survey as a committee, of course it was important to bring in all the inputs from the community. This is a community survey. And many people in the community are interested in doing dust science with Roman. Now, I should say straight away that dust is like a nuisance for many people, like it's basically trash, something you want to get rid of. It's basically your attenuation that you need to correct for when you study your favorite galaxy and you want to derive star formation, for example. But for other people, like me, this is actually what is my basically gold mine. Because from looking at dust and the dust properties, you can actually derive lots of information, and especially about star-forming regions, and so derive information about how stars and planets form. So I wanted to put the Roman Galactic Plane Survey in context. So the top plot is what I showed before. So it shows the coverage of the Roman Galactic Plane Survey. The bottom one is a figure I like very much from the paper by Tom Dane et al., which is about the CO survey that he performed many years ago. But this figure is really nice because it basically shows the galactic plane and all the star-forming regions on the plane. And what you can see is that the Roman Galactic Plane Survey will cover many star-forming regions, which are labeled here: Ophiuchus, the Aquila Rift, for the galactic centers, Lupus, and others. So why is dust so important for studying star formation and star and planet formation? So it's known that the dust extinction curve varies, especially in the near infrared, and continues to vary also in the mid-infrared from line of sight to line of sight. And in particular, towards the star-forming regions and the galactic center, there are two things that have been found again and again. So, for example, in the Betao and Nishiyama, looking at star-forming regions, I found a flattening of the extinction curve beyond 3 micron. But even more important and relevant to Roman is the flattening that has been observed, for example, by Nogueras Lara between J&H and H and K. And this is what this plot shows, that basically there is a breakpoint, which is in H band, where basically the slope of the extinction curve changes from 2.44 to 2.23. And so this is a little bit one of the holy grail that we are after when we look at dust extinction studies these days. So we want to try to understand if the dust extinction curve is, can be represented with one slope or more than one slopes due to this flattening effect. So how do we interpret, and why this is so important is because this is a sign of dust evolution and grain growth. So we know that dust extinction is a way to probe the grain size distribution. And in particular, because we are in star-forming regions, what happens is that basically the grains start growing in very dense regions. And of course, if you have bigger grains, they absorb more radiation. And so that's why there is this flattening. I'm sorry. So the problem so now is to understand how basically grains in the interstellar medium, which have a typical emerald size distribution, can grow all the way to form rocky planets in protoplanetary systems. And so there are dust models, both with ice mantles and without ice mantles, that actually predict the flattening of the extinction curve when we go to bigger sizes. So these two plots are for these two models, which are state-of-the-art models. The Themis model, which includes ice mantles, and the Astrodust model that does not include ice mantles. And the different curves are for different grain sizes. So from blue to green, the grain size increases, and you can see that the opacity flattens from smaller wavelengths to longer wavelengths. So let's come now to Roman, and here I wanted to emphasize basically advantages, but also challenges that are going to be there. So I'm going to start on the positive side, the advantages. So, and I'm going to use actually the GWST data that I've been collecting since basically cycle 1. So this is one of the objects that I've been looking at. This is a B68, so this is a prestellar core nearby, and spans an extinction that goes from 0.5 to 3 magnitude in K. So we are talking about 5 to 30 magnitude in AV. You can see, so the first image on the left is 2 mass in K. You can see very clearly the prestellar core, which is totally dark. The second image is the same two-mass band with all the Gaia sources in that region. And this is not an artifact, simply there are no Gaia stars whatsoever towards the core. And the last image is the targets of my near-spec program that I'm preparing now for cycle 4 that is going to be executed in a couple of weeks. And those are 400 sources that will be observed with the green ones that will be executed with near-spec. And there is a cut at 21 magnitude. Now, if you look at what Roman can actually detect, the estimate is that while for JWST we will have like 0.3 million sources per square degree, in Roman, in the same kind of field, we will have like 100 million sources per square degree. So, of course, this is huge. It means to have many more lines of sight, but also you can immediately start thinking that there will be lots of problems in terms of blending and extracting actually these sources. But overall, I would say statistics is going to be unbeatable, and that's one of the reasons, also because Roman will go down to 25 magnitude in extinction. That's why we gain all these sources, basically. Okay, so these are the advantages. Fantastic. The challenges. The challenges, I think, are going to be real challenges. So this is another example of my JWST program. This is S694-2. This is a collapsing core. And these are data that we collected in cycle 1. IRTF, because we didn't have the near-spec data yet. These are coming again in a couple of weeks, and then MIRI. In the red box shows the part that will be visible by the Roman Galactic Plane Survey. So the JH and K band plus the F184 filter. So this is the observed spectrum. So to extract the dust extinction curve from here, what we need to do is basically to fit a library of stellar models, but the library of stellar model has to be extinguished by extinction. So it's a bit circular, because basically to derive the extinction, you have to extinguish your target in the first place. So for example, what we do for JWST, we use the Phoenix stellar model library. In this specific case, we were able to narrow down the entire library of hundreds and hundreds of models to 77 stellar models. And then we use 5 dust extinction models to test basically the grid. And we do not introduce a broken power law. After this, we recover the stellar parameters, so the effective temperature, the surface gravity, and metallicity. But we have a spectrum. So let's come now to the Galactic Plane Survey. We are going to have 4 filters. We have to fit 3 parameters. But if you also want to fit the extinction curve, at least one power law, we have 4 filters, so 4 measurements, 4 parameters. And if we bring in the power law, the broken power law, then we have 5 parameters and 4 measurements. So this is, the equation starts breaking down. And the statistics here doesn't help. So I think this is going to be really the big challenge. Now, I just want to conclude by saying that, of course, the GRISM and PRISM would really help. So we have these 15 fields where we do the spectroscopy. And the hope is to be able, basically, to use those to leverage and normalize all the broadband photometric data. However, that we rely on our capability of being able to extract the spectra from these crowded fields, which is not a given at all. So, and in that table, I just put a list of lines that we can use to actually derive the stellar parameters, even if we have, the low spectral resolution of the GRISM and PRISM. So this is also a talk to advocate, let's say, for like more work as a community to really try to extract this data from these crowded fields. I think it really will help all this work. Sorry.
We have time for one quick question.
Do you really have to fit for every star individually, or can you group them together spatially or with parallax or something?
No, thank you for asking this question. So I think this is at the end of what is going to be done. But oh, sorry. So yes, so the answer is basically this is the only way that the problem is tackleable right now. However, I don't think it's actually a very, so it's good because it gives you the statistical information that we don't have right now. So that is going to be great and unprecedented. And so I think it's really going to move the field forward in any case. The problem is to really understand, and I speak again with my bias from star formation, to really understand what is going on, how basically dust coagulates and grows. You really need to look at the individual lines of sight and the smaller scales, because this region is 8 arc minutes. So in this core, the AK varies from, or the AV, from 5 to 30. So you can see already the problem, like you move a little bit, and basically, from line of sight to line of sight. That's the fundamental problem. So yes, you can aggregate, but when you aggregate, you're losing tons of information that is actually what you need to inform the models.
Okay, let's thank our speaker once more, please.